Good evening, students. I am Dr. Febina BV, Head of Department of Electrical and Electronics Engineering, ME Engineering College. Last class we discussed about nonlinear system. What is a nonlinear system? What are the characteristics of a nonlinear system, etc. So, this class we will look into the analysis of nonlinear system. For the analysis, we have different methods. Actually, nonlinear system will have nonlinear differential equation. So it is a hard to solve one. So we need different and peculiar methods for the analysis of nonlinear system. The two popular methods for the analysis of nonlinear systems are describing function method and phase plane method. We will see what is describing function method and phase plane method. So first one, describing function method. We use this describing function method for the analysis of nonlinear system. That is, whether the nonlinear system is stable or not, whether the nonlinear system exhibits limit cycle or not. We know what is a limit cycle. It is a characteristic of a nonlinear system. Limit cycle is oscillation with a fixed amplitude and frequency. So, by using describing function method, we can analyze whether the nonlinear system is stable or not, and whether the nonlinear system exhibits limit cycle or not. So, for the application of this describing function method, we have to make some assumption. So, the assumptions are there is only one single nonlinearity component in this system. Another one is the system is time invariant, that is the system parameters does not change with time. And it has the characteristics of low pass filter. We know low pass filter characteristics means it attenuates the high frequency components and it allows only low frequency components. The last assumption is the nonlinear characteristics is symmetric with respect to the origin. So the stability analysis of nonlinear system using describing function method. So consider a nonlinear system with unity feedback. This Kn is the nonlinear, Kn is called describing function, and the g of j omega is the linear part of this system, nonlinear system. So the nonlinear part we have represented using the describing function Kn. So the overall closed loop transfunction, sinusoidal transfunction of the system is C of j omega by R of j omega equal to Kn into g of j omega by 1 plus Kn g of j omega. So the characteristic equation of the system is 1 plus Kn into g of j omega equal to 0. So take the 1 to other side of the equation. Kn g of j omega equal to minus 1. We know by Nyquist stability criterion, the system is said to be stable if the g of j omega Kn should not encircle the critical point, that is minus 1 plus j0. So from the above expression can also written as g of j omega equal to minus 1 by Kn. This implies that the critical point becomes critical locus, that is minus 1 by Kn. At the intersection point of these two locus, that is g of j omega locus and minus 1 by Kn locus, there is a limit cycle, and we can find out the amplitude and frequency of that limit cycle also. So using this describing function method, how can we say whether the system is stable or not? By drawing this minus 1 by Kn locus and g of j omega locus, we can analyze the stability of the nonlinear system. By using a figure, we can understand it, we can make it more clear. See this figure. Figure 1, we can see both the locus, g of j omega locus and minus 1 by Kn locus. In this first figure, the minus 1 by Kn locus is enclosed by this g of j omega locus. That is minus 1 by kn locus is on the right side of this g of j omega locus. That is, it is minus 1 by kn locus is enclosed by this g of j omega locus. That means the system is unstable. If the g of j omega locus encloses minus 1 by kn locus, critical locus, then it is said to be, the system is said to be unstable. We look into the second figure. That is, the g of j omega locus and minus 1 by kn locus are there. In that, we can clearly see that the minus 1 by kn locus is not enclosed by this g of j omega locus. That means the system is stable. So, if the minus 1 by kn locus is on the left side of this g of j omega locus, that is, g of j omega locus does not enclose this minus 1 by kn locus, means the system is stable. And the third figure, we can see that the g of j omega locus intersect with the minus 1 by kn locus. That means at the intersection point, that indicates if the two locus intersect, means there exists a limit cycle. That is, this nonlinear system exhibits a limit cycle. So next we need to see whether the limit cycle is stable or not. By another figure we can make it more clear. See this. In the first figure, as the x increases, the minus 1 by kn locus is moving from the stable region to unstable region. That is, at the starting point, the minus 1 by kn locus is not enclosed by this g of j omega locus. That is, that part is stable. So, that region is stable. So, from this, x value increases. As the x value increases, it moves and it intersects with the g of j omega locus and it enters into the unstable region. That means the limit cycle is unstable. That is, if minus 1 by kn locus is moving from a stable region to unstable region, then the limit cycle is unstable limit cycle. Look into the second figure. There we can see that as the x increases, the minus 1 by kn locus moves from the stable region to unstable region and intersect. That at the first intersection point, it is unstable limit cycle. It intersects at 2 points. Am I correct? The minus 1 by kn locus intersects with the g of j omega locus at 2 points. The first point, it is unstable limit cycle. But in the second point, we can see that it moves from the unstable region to stable region. That means the limit cycle is a stable limit cycle. Okay, the third figure also, we can see that the g of j omega locus and minus 1 by kn locus intersect at 2 points. The first one, as x increases, the first one, that is, it moves from the unstable region to stable region, that is a stable limit cycle. The next intersection point, there exists a unstable limit cycle because it moves from a stable region to unstable region. So that is the crux of this describing function method. So we'll see what is phase plane analysis. Another method is phase plane analysis. It is a popular method. It is a graphical method we used for the analysis of nonlinear systems. So by drawing the phase trajectory, we are analyzing the stability of the system, nonlinear system. So first we have to see the idea of this phase plane. In the phase plane method, we are using the phase plane, that is a plane, two coordinate plane with the x1, x2 axis. That is, x1 and x2 are the state variable of the system. Normally this phase plane method is applicable to only second order system. That is, it is restricted to second order system. So if we want to apply this phase plane method to a higher order system, so first we have to approximate the model order to second order. We have to reduce the higher order system into a second order system, then only we can apply the phase plane method. So in this phase plane method, we are drawing phase trajectories in phase plane and we are analyzing the frequency. We are analyzing the stability. So this is a phase plane. In second order system, we have two state variables x1 and x2. So in this phase plane, we can draw the phase trajectories. Phase trajectory means it is the locus of x1, x2 point. So we can draw as many phase trajectories as the initial value of the state variables. That is, if the initial state is different, for different initial state, we can draw many state trajectories. So the concept is, for linear system, the state equations are a set of first order linear differential equation, and a solution of this state equation is easy. But in the case of non-linear system, the state equations are a set of first order non-linear differential equation. So solving this is a hard one. It is not an easy task. So we go for a graphical method. So this is one of the graphical method. Phase plane method is one of a graphical method. In this, we draw the phase trajectory. As I explained, the locus of x1, x2 point is called phase trajectory. Basic ideas of describing function method and phase plane method. In the next class, we will do the problems on this topic. Thank you.